Okay, welcome again everybody to the Machine Learning Coffee Seminar. Today we have Professor Jaakko Lehtinen from Monte University, who's going to talk about how to make noise out of noise, or then something else. Welcome.
Thanks, Sami. Yeah, so this is work that we presented with my colleagues from NVIDIA Research and my former PhD student Mika Aittala, who's now postdoc at MIT in ICML this summer. And forgive the catchy, well, supposedly catchy title, but it's supposed to sound nonsensical. And I'm going to talk about an idea that does seem nonsensical at first, but it turns out that it actually does work. And so, in a few more words, my topic is how to learn to take bad images and turn them into good images while only seeing bad images in the process of learning. And so the context, this is all synthetic data, but there are lots of situations where one is concerned with acquiring or somehow getting images that are not ideal. For instance, you take the Hubble Space Telescope, you point it at a region in the sky, you get an image that has noise, unless, of course, you take a long exposure. And that's what you'd want, ideally. Lots more definition and so forth. But clearly, this is expensive to do. The better your picture, the more photons you need. Another example of a scenario like this comes from computer graphics, which is sort of where I've mostly worked during my research career so far, having broadened into other fields as of late. This is a synthetic picture of a 3D scene where the light transport, how light bounces around, reflects, refracts, causes indirect effects, and so forth, has been simulated by solving certain kinds of integral equations using the Monte Carlo method, meaning that there is lots of residual noise left in this picture. So those familiar with Monte Carlo sampling know it's based on drawing random samples. And here, in this context, very literally, the more samples you draw, the better your picture. So this is 8 samples per pixel, and this is 64,000 samples per pixel. And I'm not going to zoom in, but if you look very closely, there's even with this ridiculous amount of computation put into this picture, there's still some residual noise left, even though it's a lot better, of course, than the original one. And so, okay, this is the machine learning coffee seminar, so it's supposed to be about machine learning, right? And of course, an attractive alternative or approach to a situation like this, where you're faced with, obtaining stuff that's not great, but that there's underlying good stuff in there, would be to train a model to try and turn those bad things into good things. And regression from the 39,000 foot view is having a model that you train saying, when you see this, say that, right? And in the context of learning to remove image corruptions, the simplest form of which is just noise, independent per pixel, like I showed before, this learning process entails training a model by showing many pairs of noisy images and the corresponding clean images, and trying to learn a mapping that, when given a noisy picture, outputs the corresponding clean one. Right? I should mention that there'll be examples of more complex corruptions than just independent per pixel noise later on in the talk. This is not restricted to that, even though that is the most simple thing. Very concretely, you take your model, and in our case, it's going to be a deep neural network. You take your training data that consists of pairs of noisy and clean images, and then you show lots and lots of these pairs, and you ask the model to try and reproduce that given that. An example of a different kind of corruption would be, is given here. This is a magnetic resonance image that's heavily undersampled. MRI basically takes samples of the Fourier spectrum of the volume being imaged. And here, this is the result of an MRI simulated, I'll say first out loud, that only has 10% of the information from the original. And so this is the corresponding fully sampled image that has 10 times as much information required during sampling. And of course, training machine learning model means that your ConvNet has tons and tons of parameters, and training just basically, the output of the model is determined by the positions of millions and millions of knobs, and training just means trying to find the positions for the knobs that reproduce what you want. And even more concretely, the model we use in this work is what's called a UNet with skip connections. Extremely popular architecture for image-to-image translation problems these days. Meaning that there's basically a stack of convolutions, poolings, downsampling all the way to a bottleneck layer, then going back up again, upsampling or deconvolving, terrible name, up until you feed in an image and out comes another image. And these so-called skip connections that match layers between corresponding resolutions turn out to be an absolutely vital form of architectural change that enable these models to work really well. So this is all prior stuff, nothing new here. I should point out that a very similar architecture for classification and semi-supervised learning has been proposed by local folks. The ladder network from Harri Valpola and the Curious AI folks. And so yeah, you feed in images and then stuff happens and then you get a better image out. And then the kernels in these convolutions are the knobs in your mixing table. And so what can you do? Well, it's been shown for a number of years that simple denoising problems here, there's Gaussian per pixel independent, Gaussian white noise on top of an image, and you can learn to get rid of that noise really well. That's not necessarily so exciting. That's an old thing. Maybe a slightly, well, it's a contrived example, but maybe slightly more interesting is blind text removal from pictures. This is, there's an underlying picture, and there are randomly positioned and oriented strings just pasted on top of this image. And a UNet with that kind of architecture just learns in a supervised fashion to first detect where that text is, and then remove it in paint, that text with that has content plausible, sort of fill in the underlying picture, respecting things like you see spokes in the motorcycle, and they just get filled in beautifully. Again, this is just old stuff. So that's, and then this is just a few examples. I would say that the performance of these models is at the very least it raises eyebrows, at least to me. I mean, it's quite surprising that they work so well. But up until now, we've been in the regime of supervised learning. We have pairs of bad and good that we need in order to train. But what if these clean targets are difficult to obtain? Say the Hubble example is a prime one. Like, it really takes the less noise you want, the longer you have to keep the shutter open, and clearly that's expensive. But then again, if I take different short exposures, I get different noisy, corrupted realizations of the same underlying clean image, right? This kind of noise, this work is not limited to this particular kind of noise, but this noise from photons has the property that the underlying clean image is the expectation of infinitely many noisy realizations of this process that gives out the photons, right? It basically just means that the color of or intensity of every pixel in every noisy realization of this picture is correct on average. And meaning that you just take lots and lots of short exposures, average those, and you get a result that has less noise, right? And so, as long exposures are costly, this made me think around 18. Well, it's almost close to 2 years now. What if you, let's say, you train your denoising model like this? So exactly the same thing as before. You're training a supervised regressor. There's something bad going in, and you're trying to learn a mapping from bad to good. But instead of having that clean target, this is what you should strive for, you have a different bad realization of that same thing as your target. And now you do exactly the same thing. You show lots and lots of pairs like this, and see what happens. Now you see where the name Noise2Noise comes from. There's noisy stuff in, noisy stuff out. And so these are examples of my training pairs now. So that's same underlying clean image, but a different realization. If you will, a different short exposure taken off that same scene. And then I train using this. And so we're in an interesting situation where clearly, if you think about all of these, if you think about it in the sense of when you see X output Y, this is clearly wrong. I mean, there's no way any model could learn to actually do exactly what you want, unless, of course, you have your model is way over parameterized. It has way more capacity than so that it can basically memorize your training set. But if your model is suitably sized, then this actually, even though it does seem nonsensical, it does actually work, and it works exactly as well in many situations as if you had clean targets for this training. And let me first, before showing results, let me try and get some intuition why. And so, what's in the context of zero mean corruptions like photon noise or Gaussian noise or so forth. So our clean target is the expectation of some distribution. Here all the possible noisy pictures given the same underlying clean image. Like these are all the images. These are all the ways that the central clean image can be corrupted by, say, noise. And now when we train in the standard manner, when we have a clean target for our training example, our network or our model outputs something. And basically, essentially, since we're doing gradient descent, we're tuning. I assume everyone's familiar with stochastic gradient descent and so forth. What we're essentially doing is we're computing the loss. We're saying, well, how would the network prediction have to change so that it became closer to the clean target? And this gives us a gradient with respect to the parameters of the model, saying that if I tweak these parameters in such and such way, my prediction is going to go closer to the target, right? I mean, this is again just pure simple supervised learning. Now, if on the other hand we give targets that are not correct, but that are correct on average, then it turns out that the average of all of these gradients, well, all of these training examples, they give us an erroneous, a false gradient. The gradient at none of those training examples actually points to the right direction. But on average, because these targets are drawn in from such a distribution that their expectation is correct, on average, their gradient will actually point towards the right direction. So at least, this is all hand wavy at this point, but at least given infinite training data, and if your targets are correct on average, then the expected gradient is correct, and the optimum of the learning problem is actually the same as if you'd observed the clean thing. However, at no point in this process do you actually observe the clean target. And so, from the statistical point of view, if I give you conflicting goals, and I try to minimize the squared loss, then we all know from basic statistics that the mean is the point that minimizes the expected square distance to whatever you're seeking. And in this case, really, the only thing our model can do, provided that it actually finds this optimum, is to find the expectation of all of those noisy targets, which is exactly the result that we're looking for, if our corruption happens to be zero mean. And so the upshot up until this point is that we can learn to denoise images, take bad images and turn them into good images, without ever having seen what a good image looks like. And this does not well, we can do it just as well as if we had clean data. I'll show that we can actually sometimes do even better, which is very surprising. But that is the case. We can do it as well or better. And we can do this without an explicit statistical model of the corruption in those images. I don't need to know if the corruption in that image is, say, Gaussian additive noise. I don't need to know if it's Poisson noise, that is to say photon noise familiar from the cameras. I don't need to know if it's brown noise, take Gaussian white noise and blur it spatially so that the frequency content is different. In all of these cases, the only thing I need to know is that the answer, the distribution of those training samples is such that the expected value per pixel is correct. And that is true for all of these different corruptions. It's also true for the MRI case that I'll talk about in a little bit. And so that's rather remarkable. I always thought. Examples of real world uses, again, this is a graphics application, this is a realistic rendering where unless you take lots and lots of samples per pixel, which is obviously it scales, computation scales linearly with the number of samples per pixel, this is a denoising result given images only that look, bad like that. And you can learn to turn that into or remove the noise and turn it into a good image. And I'm not showing the comparison to a model trained using clean targets, because it looks basically essentially the same. And this is our ground truth result, and which has been computed by using lots and lots and lots of computation. And so that's a real world use case. We've trained also, up until now, the intuition is all built on using infinite data. It turns out that finite data works really well as well. Here's an example of denoising real astrophotos, amateur astrophotos, which, well, again, naturally contain a lot of noise. It doesn't really matter that the details are not visible. The point is that it removes the noise really well, on exactly as well as if you had those clean targets. And funny enough, astrophotography is a natural fit to this model. We need two different realizations of the same underlying clean thing so that we have different corruptions on them. So for photos, we need two different photos that have a different noise pattern. And this is as it turns out, this is something that astrophotography is doing all the time anyway. They point their telescope at the sky, then they track it using an equatorial telescope mount, but they don't take just 1 hour long exposure for the reason that tracking is never perfect. You'd always get some residual blur in the image due to motion. So what they do instead is they break that hour long exposure up into lots and lots of shorter exposures, and then they align and stack them to remove noise. And so we basically get data that we can use directly from that process. Now here's something that up until now it's useful for graphics and potentially useful for astrophotography, but this is an application I'm really quite excited about. So MRI, like I mentioned in the beginning, it's people way smarter than me know the physics and how it actually works. That's basically all magic, as far as I'm concerned. But from the mathematical point of view, what MRI does is it takes, you have a volume you want to image. And it turns out that the machine takes essentially point samples of the Fourier spectrum of the density in that volume you're trying to image. So each sample taken by that machine is a complex coefficient that corresponds to one particular spatial plane wave in that 3D volume you're imaging. And so now, what we've done here so far in simulation is this is a 2D frequency plot. So the DC term is in the middle. That's the I assume you all know what the Fourier transform is. And what we've done here is we've constructed a Poisson process that either keeps or discards a frequency based on not a Poisson process, but a Bernoulli process that either keeps or discards a given frequency with probability that's high in the center and falls off towards the sides. And the frequencies that we don't keep, we set their values to 0, and frequencies we keep, we multiply by the inverse of the probability that we kept them. And so it means that the expectation of this process is actually the correct spectrum. If for one particular frequency, if 9 times out of 10 I decide to discard it, then the one time I keep it, I'll just multiply its value by 10. And then again, when I take the expectation over all possible realizations of this process, the spectrum is correct on average, right? And so here's just two different random samplings of the space of FFT. It's called K-space in MRI. And these are the corresponding images. If I take these spectra and I do the inverse FFT of those point sampled spectra, in each one of these, only 10% of the frequencies are actually retained. 90% of the information is lost by this selection process. And so these are the images that I get if I just do an inverse FFT from that undersampled spectrum into the primal domain. And so we can see that clearly there's lots and lots of noise and artifact of different kinds. There's low frequency artifacts as well. There's sort of waviness in the intensity of that noise and so forth. And so if I compare these two images like so, you see that they're really really quite different. But again, clearly there's something in common as well in these images. And because if the spectrum is correct on average by construction in our sampling process, the Fourier transform is linear, and linear operators have the property that they preserve mean. Meaning that when I take those undersampled spectra and I do the IFFT, then in the space of pixels, these images are correct on average as well. On average, the value, the intensity of every one of these pixels is correct. Again, it's just because of linearity. And this means that our assumptions apply. I have pairs of images that are bad, but that are correct on average, and I can train with them. And it turns out that when I do this, I learn again precisely as well to reconstruct good MRI from bad MRI. Exactly as well. Well, this some points of a decibel is random fluctuation, and we actually now get numerically better results with a new network model. Point being that in this sort of application, there's no gain from having clean data available to you in learning. And so that's I should point out that this is not diagnostic. This is not clinically proven. It's working in simulation. We start with already reconstructed MRI images. We simulate the sampling process, and then we train. But we've tried to be really careful in talking to MRI experts, making sure that our assumptions in that process are correct. And now we're actually traveling to the West Coast to talk to some of the best MRI people in the world in a month to try and see if what they think about this. So long way to go. Like I mentioned, it's not as good, but it can be better. So in particular, if you consider the realistic situation where you have a fixed budget of capture, you only have some amount of time or money or resources you can use for capturing your training set. Now, in the traditional training regime, when you have clean targets and noisy realizations, each target is expensive to capture. You need to keep the shutter open for a long time, and then within a fixed budget, maybe you can afford 2 training examples. You have 2 things that are on the manifold of clean images, but because each one of these red dots is super expensive, within a fixed budget you can't maybe capture as much. It turns out that if instead you slice your capture budget in a way that you do more underlying clean latent images and only capture 2 cheap samples for each one of those, within that same capture budget you can clearly sample the underlying manifold of clean images that you don't observe at this point, but you can clearly sample it better. And we have synthetic results in the paper showing that for at least Gaussian noise, this is a net win. You get appreciably, not just in terms of PSNR, but visibly appreciably better results when you train using this bad stuff than if you do with good stuff. But a full study of how far that goes in each domain and so forth is still to be done. I mentioned it's not just for zero mean corruptions. To recover the mean, you optimize the L2 loss. I mean, that's basic statistics. Basic statistics also says that if you want to recover the median, component-wise median, you optimize for the L1 loss, or mean absolute difference. And so this is an example of learning to in-paint, the same image, the same thing, learning to in-paint random text from images, but trained only by seeing images that have random text. It's never seen a clean image. It's only seen images that have different random overlays of text on them. But again, the text, there's not so much text that over all of the training set, on average, the color of every pixel is correct. More than 50% of the time in a training picture, each pixel is going to have a correct value, meaning that the median is the one we want. And the only thing we need to do in order to train for this is to just change our loss from L2 to L1, and then we recover. Then we learn to do that. Again, no knowledge of where the text is and so forth. We can do the same thing with sparse inputs. So this is sort of the thing we had in MRI, but in primal domain. Here we only have some small fraction of pixels observed, and we train with pairs of images that look like that. And then we learn to recover just based on the same math. This is the L2 optimum that we get. And of course, it's not perfect, but it's pretty good. The final example is even heavier corruption. So in this example, we've 70% of the pixels are replaced not with zeros, but with actual random noise. Pick 70% of the pixels at random, replace their value with a uniform random number between 0 and 1. And now the mean is not correct. The median is not correct, since 70% of the time each pixel has the wrong value, and it's completely random. But the mode of that distribution, you take a pixel, you look at all the different corrupted versions of it, 30% of the time it will still have the correct value. So the mode of that distribution is the correct answer. And we can engineer a special kind of what we call a mode-seeking L0 loss. That's not truly the L0 loss, but something like that. And we can learn to reconstruct that image from that input, again, while never having observed what good images look like, only that bad stuff. I have no idea. This is not a realistic corruption that we know of. We just thought that, okay, let's make this really hard and see where we can push it. And there are some other extensions in the paper. It's time to conclude. What I've shown here is quite a universal mechanism for training image restoration models that look at bad stuff and I'll try to remove corruptions. What I find powerful is that we really don't need to know anything about the corruption except the statistic of inference. Is it correct on average? Is the median correct, and so forth? We do not need an explicit statistical model of that corruption. We don't know if it's Gaussian or Laplace or anything like that. The same thing works out of the box for you just give it different data. And there are situations where reference images are hard to obtain. I've mentioned low light photography and astronomy and MRI. And our applications to computer graphics mean that, well, and all of this means that this has, well, at least we hope, it has large implications on how easy it is to actually train high-performing image restoration models, since you don't have to put in as much effort into gathering your training set. In our graphics example, the model that works as well as the one you trained using clean targets took 2,000 times less effort into creating that training set than it did if we used clean images. Something that makes me really happy is that the first applications of this are coming out. These are some MPI folks from Dresden. And in the ICML poster session, lots of people came up saying that, well, we have this biological imaging regime where we can't shoot out a lot of photons or whatever illumination they use because we'll kill the specimen. Cryotransmission electron microscopy is an example where you take microscope images of something that's cooled close to absolute zero, And they also can't use that much light because it'll thaw the specimen and bad things will happen. But they've taken this stuff just out of the box. Say they dramatically increased contrast, furthermore automated downstream processing of restored images, and segmentation leads to improved results. And so this is sort of the kind of gain they got from just using it out of the box. This is their standard state-of-the-art reconstruction technique, and this is their initial result using noise-to-noise training. Lots and lots of more definition, all the features much better visible and so forth. That's what I have. I'm pretty excited about this. Happy to take questions. I think in 10 minutes.
Looking at compress sensing, so you have this kind of a multiple filters that produce random kind of a corrupted images of the thing that you are taking. Usually you need kind of 100,000 of those in order to actually build an image. But here what you have is a pretty nice trick that every specimen that you only have two different kind of images out of the thing. You can combine the result from multiple images when you do the training that actually. And then the local behavior, all of those images are the same.
Exactly.
And you do the L0 kind of recovery again of the image that is coming out.
Yeah, in that one particular example,
Yes.
L0. Yes, correct.
So, and that actually sounds pretty much the same thing, but it actually has a nice thing that you can actually use this compressed sensing for different images, and then still get out the kind of system.
Compressed.
This is what I think that what is happening.
Yeah, compressed sensing that's an inspiration, of course. The difference there, though, is that in order to derive the reconstruction technique, you have to have exact knowledge of the properties of the signal you're recovering. Yeah, exactly. The exact form of the corruption is implicit in the data, and that's learned by the model. We're actually getting. I feel we're getting a little bit flack from some communities for basically coming in and barging and trying to solve their problems in a stupid way, because, well, I guess for obvious reasons. But there is a lot of practical value in having a model that you just take and it applies to different scenarios without you having to do that much, I would say.
How many different images, noise images, from same perspective do you need to reconstruct a reasonably good image?
Well, at test time, just one. I mean, it depends on, and the result is exactly as good as if you trained with clean images. Are you talking about training time?
I mean, training data.
Well, our studies are limited, but for additive Gaussian noise, blind Gaussian denoising, meaning that you don't know the magnitude of the standard deviation of the noise, there the optimum is 2. It's better to take 2 bad images and more underlying clean latent images than it is to take a better image of each underlying image. Yep.
Have you studied the noise of this magnitude of the noise, like the variance, versus how many samples you need, or some sort of properties like this?
Not really fully pushed it where it should go. Clearly, if you have,
if you have a lot of noise, I guess you need more samples.
Yeah. But that's also the same for training with clean targets.
Yes.
But we haven't done a full analysis of this. I mean,
you have this combinatorial explosion because you use noisy for the output input. Maybe you need less. Maybe it grows less for your case.
Clearly, like in the limit, you have a picture or MRI where you retain 1 Fourier coefficient. It's still correct on average, but your data is going to be total garbage. It's going to be harder for this to learn, but that's kind of academic since it's not going to work even with the clean data. We haven't really fully mapped out this space, I have to admit though.
Do you have an idea of the ratio?
It depends. Well, answer is it depends. It depends on a lot of factors. There's nothing general I can say.
Have you tried it with different context images? I mean, that if you train and set a network with images of birds, noisy images of birds, and then if you apply it into astronomical images, then does it produce birds there instead of stars?
That's a great question. If we train on a restricted class of images and then try and transfer to a different domain, what kind of artifacts do we get? We haven't tried that.
And then also what happens if you adjust the width of the bottleneck in this U network so that you can tune how much information you have in the image.
Well, the UNet is not a classical autoencoder in the sense that there's these skip connections.
Okay.
The dimension of the bottleneck is, we haven't studied that there because the model we use here, the point is like what is the training data? We've tried this on a couple of different architectures and it all works. But the point is really like just feeding in different data and seeing how you perform. But so that's not given the skip connections, that's not a crucial design point. I should say that if you try to do any of this, even with clean data, without the skip connections, you're not going to get anything reasonable.
So the skip connections are somehow like important to catch details.
Yes, exactly. You cannot, no model that we are aware of is actually able to reconstruct good detail in the output if you don't have those skip connections.
But there's still some like limited bandwidth that the network can pass information. So that if the bandwidth is too high, then you will get noise in the output as well. But if the bandwidth is too strict, then you will catch enough detail.
Yeah, this is the trade-offs here are the same as with supervised learning with finite data in general. Like too large a capacity combined with training set that's too little will lead to overfitting clearly.
Thanks.
I think about the case when the average is 0, but I mean they have bimodal distribution. So in that case, I wonder what about the accuracy of the methods you have present. I mean now they have the 0 mean, but they have 2 distributions like this. I mean bimodal, and now mean in middle, but you have 2 peaks. So now in that case, it's very complicated, and I don't know what happened now.
We haven't tried that. Can you give an example of a corruption where that could happen?
Yeah, here in the case you consider Gaussian or Poisson just unimodal.
Sure, I understand, but can you think of what would be an example that exhibits that kind of behavior? That's what I'm asking.
Maybe in some biological system, like they have switching behavior.
Mm-hmm.
They switch from when some signal happens, they in this state, in other state.
Mm-hmm.
So in that case, I don't know. This is stochastic system, and in that case, I don't know what's happened here. They just take some picture from this and reconstruct using the system you are using, and I don't know what happened.
Well, this sounds like something we should try. I mean, if you have ideas on actual corruptions that exhibit this behavior, then that would be highly appreciated.
I think it's maybe a different domain, but you could mix 2 pictures.
How do you ensure that the average is correct?
I don't know, but I think this is a different, because you're doing noise, completely noise, but this would be a different problem, I think, where you've actually got 2 pictures and they're overlapped, and you have to a distribution for both, and you have to learn both.
Yeah, we've had an example. It's the text and the image detector. That's 2 different images.
Yeah.
That are mixed into one.
Yes.
Oh, okay, so now we have.
But that's still that has a single mode at the.
Yes, it has a single mode, so adding pictures doesn't actually create necessarily too much of this.
Yeah, but anyway, I'm really glad to listen to more ideas. Yeah.
So in the case where you don't have like a true image, so usually when you do hyperparameter optimization, that you sort of train the model, test on some validation set, and then tune the parameters to sort of give better results on the validation set, and then finally do it on the test set. in the absence of a true image, how do you do hyperparameter optimization?
We don't. The thing is, that's a great point. You could, of course, if you wanted, we've only compared how does it perform with the exact same parameters and architecture if you just switch the training data. So that's sort of a controlled thing to try. You could, of course, if you wanted to do classic validation, you could capture a validation set, a small validation set, and put in more effort so that you have the actual ground truth labels for that, so that you could then use in the way you described. But since the set is way smaller than your training set, you're still going to save a lot of time in the capture. That's a great point.
I think we are running out of time now, and we'll need to thank Jaakko again. And if there are further questions and Jaakko is around, feel free to try to grab him.
Yeah, all ideas welcome. Thank you.
Thanks.